A few months ago, me and my girlfriend, we were at the lounge and we were sitting together and there was no one else at the lounge. You know what we did? We studied mechanics. Like the good students of KYUEM we were. Alright, so we were going through the course book and we stumbled upon this particular example. So it looks like your normal mechanics diagram, nothing to be scared about. There's a lot of words, there's a lot of G's, and there's X's and Y's. So it seemed normal until you take a closer look at it. So if you look at here, the G is actually working vertically, which was how the universe is supposed to work. Gravity makes things fall, so things fall vertically. But there's also G in the X direction. So that means that gravity is apparently working sideways, which didn't make sense to me, and that bothered me quite a lot until I actually figured it out. So, the reason for that is actually because instead of the paper being vertically like this, it was actually horizontal like this. So, when the G is working vertically, it means that the thing is hinging like that. And on the x-axis, the G is hinging like that. You get what I mean? Yeah. So, and it was revolutionary at the time because it made sense. Like, I actually understood what I actually learned. And so, I wanted to explain it to her in a way that made sense. But what actually happened was, I went to her the next day and I told her, hey, the diagram is wrong. It was actually like this. Do you get it? So then she had this look on her face that tells me that she regretted dating me in the first place. But anyway, the point being that textbooks don't really give you enough to make you understand the stuff that you learned. Or in other words, I'm teaching you how to not be content with your syllabus content. It's fancy, in fancy words, it actually is redefining maths and all that stuff. And so, let's take a step back a bit, and I want to reminisce my time during high school. I wasn't really good at maths in high school. I struggled a lot in maths in high school. I don't know how to use air quotes properly, as you can tell, but during high school, I always wondered why certain things are the way that they are. So for example, right, when you calculate the arc length of a circle, I always wonder why we have to use radians instead of degrees. It just seems like there's a lot of work. I have to convert degrees into radians first, and then my teacher is telling me that I cannot use radians in trigonometric functions, and all of those didn't make sense. And the more that I learn about maths, the more that I don't actually understand. And the more that I don't understand, the more that I'm not feeling satisfied with what is it that I learned. Like, look at this compound angle theorems. They never explain to us how is it that sine A plus B equals to all of that stuff. And yeah, it is a bit much to remember and memorize all of that stuff. And you know, I'm also struggling with my bad handwriting. My teacher is always telling me that I'm having bad handwriting. So life wasn't really good. So I decided to make it a turning point in my life. I need to know why we use radians in calculating the arc length of a circle. And so here's what I found. So, in defining a circle, the circumference of a circle is 2 pi r, right? And so if you divide it into 4 parts, you make 4 sectors. And for that each part, the arc length of one sector will be 2 pi r divided by 4, which is half pi r. So that's a more natural way of defining the angle of the circle, by using 2 pi as its unit, because it feels more natural that way. And so 360 degrees, it's really an arbitrary number. And from that, what I discovered is that there are 3 different methods of defining angles, which are the degree, which is when you split the circle into 360 parts, the radian, when you split the circle into 2 pi parts, and the gradient, when you split the circle into 400 parts. So you can split the circle into how many parts you want, 1000, any number that you want. But one thing led to another, and I found myself actually in a propaganda document talking about why we should use tau instead of pi. And so for those of you who are curious, tau is actually 2 pi time 2 pi. So why it deserves this long of a propaganda document, never mind, why it deserves that long of a propaganda document really makes me feel like I don't actually know maths, but that's fine. So I want to tell you a way to learn things in a more satisfied manner. And that way is to always have first your motivation, second is your content, and third is your application. And so let's start with a very simple explanation. Quadratics. All of us here love our quadratic equations, right? So let's start with the motivation first. There was once a guy who went to Goldman Sachs, and as soon as he opened the door, the interviewers asked him, "Oh, can you factorize 143? My guy was stunned because there was never a time in his life where he thought that he would have to factorize to get a job at Goldman Sachs, at all places. So he thought about it for a while, and he said 13 and 11, and he got the job. Probably not because of that one question, but can you imagine how bad of a first impression that he would have given off if he didn't get the answer? So you might think to yourself, okay, that's cool and all, but how does that relate to quadratics? So essentially, you can factorize x squared minus 1 into x plus 1 and x minus 1. And so replacing the x with 12 gets you 143 equals 13 times 11. And so this works with everything. Let's say you want to factorize 168, which is 1 less than 169, which is the square of 30. So you would get it to be 12 and 14. So then, after building up the motivation, now the students have some sort of motivation to go through the content. Content-wise, I think that most syllabus do a great job at laying the foundational bricks. But I still feel that quadratics, they don't introduce you to graphing calculators. And so what I want to show you here is that for quadratics, by introducing the students to a graphing calculator, you can figure out the things that dictate how narrow the curve is, the position of the curve along the origin. For example, the B coefficient actually dictates the position of your curve around the origin, and also your C dictates the y-intercept. And so by using a graphing calculator, you can really get a lot of insight and a lot of intuition about how the quadratic formula actually functions. And then after moving through the content, you can move on to the application. So have you ever wondered if you can actually do a whole maths paper by using your hand only? I have, but definitely not your A-level maths paper lah. But in order to do your maths paper by hand, you would have to figure out how to figure out the trigonometric functions by hand. And so this is where something called the Taylor series actually comes in. So the Taylor series is a polynomial representation of what a function should be. This is the polynomial representation of the sine function. And so as you can see, technically, if you're a human calculator, you can figure all of this out by hand. But I am not a human calculator. The fact that this exists already awes me. And so now I actually know that you can do trigonometric functions by hand. And so that's how you introduce students to the applications of quadratics. We talk to them about polynomials and the applications of polynomials. And so, annoying slides out of the way, what is it that I'm actually trying to tell you here? Well, all of you here, KY students, all of you are really bright people. And you have great teachers, you have great resources, you have great friends. There are people out there who don't have the same resources as you do. They're not as lucky as we are. And so these people, they need guidance. And that guidance can only come from people who are really passionate about what they're learning, about what they're sharing. And so that's what I want from all of you here. To be more passionate in what you're learning so that you can share your learning experiences with everyone else. But not only that, things are changing. The world is changing for the worse, if I'm being frank with you. There's climate change, there's poverty, there's other stuff happening in the world that needs attention, that needs urgent solutions. And those urgent solutions don't come from a place of this passionism, you know? You need people who are really passionate to be able to come with really great solutions. And that's where all of you guys come in. Bright people with passionate things to do. But it's easy to feel overwhelmed. After all, I'm here giving a TED talk about maths when I realize that there are other people who are smarter than I am that should be talking about maths than me. But learning is not about what you already know or what you have known for a long time. It's always been about sharing. It's always been about trying to collaborate with other people who are as passionate as you are. When you have a hard problem, you come to people and you become interested in the way that they solve the problems. So I want you guys to look at a hard problem and not think about, oh, only smart people can do this problem, only smart people can think about this problem. Try to unlink the maths from the person itself. Try to fall in love with the process of problem solving instead of who can problem solve. In that sense, you would find a greater satisfaction in finding problems that you can't solve. Because it's less about who can do it, but it's more about how to do it. And falling in love with the process of problem solving. And so, yeah, if there's one thing that you should take with my speech, that's to always have motivation, content, and application in everything that you're learning. That's actually 3 things. It's amazing how the further you take your maths, the more that you rely on your calculator to do these basic things such as counting. At the end of the day, if someone comes up to you with an interesting problem or an interesting topic to share about, don't just see who cares. Who knows, that one thing might land you a job at Goldman Sachs. Thank you for listening.